software-defined radio, and basically the work I'm currently doing, trying to implement an autonomous device for SDR based on the Parallella. So I was a Kickstarter backer, and thanks to Andreas, I basically got all the revision from the prototype to the revision 1 and final Kickstarter board. And when I first backed the project, I didn't really have an application in mind. And what I decided to do with it is basically exactly that, some kind of software-defined radio device that's autonomous. I can carry it around and use it without the help of a laptop. So the requirement for this device is it has to have some good processing power. It has to be portable. It has to be operated on battery. And obviously, it's going to need some peripherals, things like screen, obviously some kind of a radio interface since it's a SDR device, and basically some user interface stuff.
セベンは、ソフトウェア無線について SDR についての話なんですけれども、こちら彼の環境とか、使っているものですね。
Okay, so why do I think that the Parallella is a great fit for this application? Well, I said that I needed a lot of computational power, and the Parallella has plenty of that in 3 main aspects. First, you have the FPGA, the Zinc, which is going to be great for very high throughput application. You probably want to keep the stuff that you do in the FPGA pretty simple because coding for FPGA isn't especially easy, and it takes a lot of time. But it can go very, very fast. Then, of course, you have the Epiphany, which is kind of a middle ground between the FPGA and the ARM, in that you program it with software, which means that you can iterate you have a very fast development cycle and easy tools to debug and that kind of stuff. It might not reach the peak performance of the FPGA, but it's compensated because you can do much more complex application more easily in it. Then at the lower end, you have kind of the ARM, which is great for control of the just scheduling and the higher level of a protocol stack, but not much for hardcore digital signal processing. The FPGA is also low power, which you definitely want for battery operation. And finally, you have GPIOs, lots and lots of GPIOs, because as I said, I'm going to need a lot of peripherals, and so I'm going to use those GPIOs to connect also those peripherals.
でこれ3つの観点から、私が重要視しているところなんですけども、FPGA、エピファニー、ARM の方はスループットやコントロールができるというところで、あとローパワー作ればパワーが使いすぎないところがいい。あと GPIO はペリフェラルがいっぱいあるので、いっぱい使えるのがいいというところですね。
Now there are also some, limitations to the platform. The Parallella is not perfect. I said it has lots of GPIO, but I also have a lot of peripherals to connect, and so it turns out I can't just connect them in the simplest way possible. I have to be a little tricky and basically use them wisely. Those GPIOs, you can also control at which voltage they operate, but you can only choose one voltage. You can't have one GPIO operate at 3.3 volt and another operate at 1.8 volt. That doesn't work that way. So that may require some level shifting. One of the big downsides is that there is no MGTs. So Xilinx FPGA, some of the higher hand ones, have what's called multi-gigabit transceivers. And those are I/O that can really, really go fast. I mean, we're talking multi-gigabits on a single differential pair here. And that could be used to implement things like SATA or GSD204B, which is a protocol to talk to digital and to analog converters, and display ports as well. Another downside is the ailing bandwidth, although that should be fixed soon, right? Hopefully.
GPIO たくさんあると言っても48なので、ちょっといろいろ使い方に工夫が必要であるということと、ボルテージ伝 つかなは、固定になってしまうので、5と3と 3.3 を一緒に使いたいとかそういうことはできない。あと、NoMGT ということで、SATA とか EDPA とディスプレイポート、あと JSD のようなアナログデジタルのコンバーターとかが今はない。最後に E-Link も、固定になっている。バンドレスが帯固定になっているということです。
So the first peripheral I worked on is the interface to the screen. I wanted a very nice screen, and so when you're looking, at what kind of LCD panel you can buy, you're gonna find three main kind of interfaces or to talk to them. The first one is the parallel, just a parallel bus, which is very simple. You've got your red, green, and blue signals. It's super simple. The downside is that it's not very popular for high resolution panels because the interface just can't push enough data through, basically. At the other end of the spectrum, you have DisplayPort, and especially the embedded DisplayPort variant. That's the kind of interface you're going to find on your latest iPad Retina display, most likely as an embedded DisplayPort interface. The bad news is that these are very fast serial links, and the GPIO on the Parallella can't talk to those. You would really need MGTs, and that's where they would be really useful. And kind of between the two, you have something called MyPy DSI. It's also a fast serial link. I mean, it's a DSI is a display serial link, but the frequency is slightly lower, and we're talking, a few hundreds of megabits per second per data lane here. You can't directly connect them to the Zinc, but with a few external components, it's possible to do it, and I will show that later.
これは全部 LCD のタイプについての、3つのタイプなんですけど、最初パラレル。これは簡単、シンプルで、そんなに、そうですね、最近の高解像度には対応しません。あと EDP、エンベデッドディスプレイポート。こちらは早くてジンクに対応はしてますかね。で、これを使うには、やっぱさっき言ったように MGT いろいろ必要なんですけれども、ないということで、パラレラではないですね。で、最後に MyPyDSI っていうのが、早くて、ただ、ジンクに直接つながらないんですけれども、ちょっとした、内部のトリックでつなぐことができます。
So as I mentioned, you can't just directly connect those to FPGA IOs, and that's because on usually you have a binary digital signal which has only a 0 level and a 1 level, but on the MyPy DSI signals, you have 4 possible levels. It's kind of described there, but what's important to know is that each data lane that actually transport data has 2 possible modes. What's called the low power mode, in which it's low speed just for control and stuff like that, and it's just 1.2 volt signaling, standard stuff. And then the same data line can actually also operate in what's called high speed mode, and that's a differential signaling, and you have to be able to switch between the 2 modes dynamically, which is something that the FPGA IO can't do natively, basically.
MyPyDSI というのには、デジタルのように0と1ではなくて4つのモードが使えるので、下に4つ、ライトポイントありますけれども、その中でも上から3番目 LP もローパワーモードと4番目ハイスピードモードで切り替えができることになります。
So this is basically how you would do it. Is you for each IO, for each differential pair of your MyPy DSI signal, you have to actually use 4 FPGA outputs. 2 are going to be dedicated to driving the low power mode, and 2 are going to be dedicated to drive the high speed mode, basically. And then using a combination of resistors, you can somehow drive the correct signals. And if you do all the math, you'll see that it works out. これは Parallella の 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 Parall the advantage of this solution is it's very simple and it's very cheap. I mean, all you need is basically like 6 resistors that cost nothing. The downside is that, well, you're using a lot of GPIOs. For 4 lanes MyPy DSI, you're gonna need 20 of them, which is almost half. And another big downside is that in what's called the LP11 state, so this is low power 1 is both outputs are set to 1. This is basically the idle state when the link does nothing. If you look at the schematic, you'll see that in this state, you're actually burning power because you have a resistor divider to ground. And so in low power mode, you're actually burning 8.5 milliamps per signal doing nothing. So you have a low power mode, which isn't low power at all. So yeah, we're going to need to fix that.
これはレジスタ6個とかでできる簡単で安い方法なんですけれども、GPI をたくさん使ってしまうし、ローパワーと言いつつもそんなことはなくいっぱいパワーも使ってしまうという欠点があります。
So it is an improved version. It's basically the only difference compared to the previous version is the value of the resistors. I've changed a little bit, but instead of using a simple resistor divider to go from 2.5 volt to 1.2 volt, we're actually using an external level shifter, something that's going to take the 2.5 volt that's output by the FPGA and convert it to 1.2 volt. One of the downside is that, well, the component you don't just have resistors anymore. You have actually level shifters, but they're really cheap. They're really small. I think the level shifter that I use are not bigger than the resistor packs that I use, so it doesn't really take much space. So it's still pretty simple. It's still cheap. I have a low power mode, which is actually low power. And there are also some advantages, is that the LP drivers for the lane 2, 3, and 4, they will always output the same data. That will never change. So you can actually share them. In the previous version, you couldn't really do that because if you look at the resistor arrangement, it would have created crosstalk and some weird stuff. But the details aren't really important. What's important is that you can now share those signals, and so you can diminish the total number of GPIO you're going to need to 14, which is much more reasonable.
これ先ほどのにちょっと改良を加えたものなんですけれども、だいぶ良いところが増えて、安いのはそのままで、ローパワーは本当にちゃんとローパワーになっています。あと、レーンの2、3、4のところで、信号の共有もできますし、GPIO を使う数も多少減ります。
So now that I know which interface I want to drive, I had to actually pick, an actual screen to drive. I settled on basically reusing the Kindle Fire HD 7-inch screen, because reusing a common tablet screen is good because you can buy replacement display assembly from eBay. So they're cheap, they're available, because at least where I live, I can't just go down the street and buy an LCD panel. It's 1800 by 1280 resolution. It has a 4-lane interface. I chose it because the datasheet is available. The datasheet is in English. Yeah. I also know the connectors because it's the datasheet actually tells you which connectors to buy, and that's a connector I can actually buy. It's available at DigiKey. Another thing is that the Kindle bootloader, which is also U-boot, is open source, and that actually turned out to be pretty important because those screens, all those modern screens, if you turn them on, by default they do nothing. You actually have to kind of boot them and send them initialization sequence and all that stuff, which isn't in the datasheet, but it was in the code of the bootloader. This screen also has a touch screen, a digitizer, and the good thing about this is that the controller for the digitizer is included. There's no datasheet for it, but there's a GPL kernel driver that works. So I was happy with that.
それで、Kindle Fire HD を LCD ディスプレイとして使います。で、これの LCD としてのスペック、そういうところなんですけども、データシートがあるので、 いろいろ細かいところは分かります。あと、コネクタとかも普通のものが使えます。で、Kindle のブートローダーは U ブートなので、それも、オープンソースで今までのと同じでいいと。あと、実際ザーを含んでいるところも良いです。で、これについてはデータシートはないんですけれども、そんなに難しいことはなく、GPL のカーネルドライバーも使えます。
So yeah, it works. That's basically a picture showing, I think, the trailer for Star Trek.
これ使っているところですね。
So the second peripheral I started working on is, well, the actual software-defined radio interface. I decided to use the Myriad RF module, at least at first, because I didn't want to deal with two things. The first is that chip has a really weird package. It's like a QFN with 2 row. It's really hard to solder by hand. And given that the chip costs like 25 or 30 bucks, I didn't want to burn one. And I wanted to avoid to deal with the actual RF part at first. The module is available. You can buy some, and I had 2 of them already, so that was good. And finally, I really like the fact that the company that makes this chip, the LMS 6002D, they're really into open source, and so all the documentation is open. There's a bunch of code that's already available because there are several open source projects like the UMTRX and BladeRF that use the same chip, and so I can reuse a lot of their code, hopefully.
今はこの、ミリアドの RF モジュールを使っております。で、変なあれがないっていうのと、そうですね。一番安いんではないんですけれども、使いやすいということで使っております。
Okay, so as I said, I can't just take. I think there's actually a Parallella project that already interfaces the Parallella with this particular Myriad RF board, if I'm correct. Andreas, do you? Right. Yeah. Yeah. Exactly. But what they did is they basically took the simplest possible way of connecting this chip to the Parallella, which is obviously a good choice for them. Unfortunately for me, that doesn't work because this would use too much GPIOs, and again, I need to use them wisely. So if I just connected the signal as is, it would take 14 signals for RX and 14 for TX, which would make a total of 28. And I just can't spare 28 GPIOs. I don't have that much because I have all those other peripherals to drive. So the solution is to convert the all the parallel signal into a high-speed serial data stream, and I can do that using external SerDes chips. I selected some from TI, and basically they will convert 14 signals into 3 differential pairs. So for RX and TX, I now just need 12 GPIOs, which is much more reasonable. As a bonus, those chips will actually do the level conversion for me because they accept LVDS 25 on one side, and they output CMOS 3.3 volts at the other side, which is exactly what the Myriad RF needs. Obviously, there are some downsides. I mean, those chips aren't free. They actually, cost something like $4 or something. It will cost some power, it cost some space, but that's not too important. One bigger concern that I haven't actually worked out yet is the phase noise. Basically, when the FPGA is going to send data for transmit, the Myriad RF is going to receive that stream, and the clock that's actually going to clock the digital to analog converters is going to be a recovered clock by this PLL. By this PLL there. So it's a recovered clock, and I have no idea how much jitter or much phase noise it's going to introduce. It shouldn't be too bad, but it's still something to watch for, basically. I basically assembled a prototype that has this last week. I haven't actually tried it yet, so that's it.
じゃあ、さっきのボードを使ってですね、いろいろやっているんですけれども、いいところ、悪いところあって、そうですね、電圧のところ 2.5V、3.3V のコンバージョンができるところなどもありますし、悪いところとしてはちょっとお金もまだかかってしまうのと、あとクロックですね。で、フェーズノイズが出てしまう。そこを注意しなければいけないということ。で、現在のところでは先週プロトタイプを作って、というところです。そこまでそんなにはまだやってないんですけれども。
So it is basically the prototype I've been working on. You can see basically damn it, the serializer and deserializer chips, and here you have the screen interface and the actual PHY, which is there. As I said, the display is working. You saw the picture. It still needs some work on the FPGA side. The SDR, I'm basically just starting the testing on this.
じゃあこれが先週作ったというプロトタイプのところですね。これからテストを始めます。
ありがとうございました。で最後に、RS の宮原さんの方から